Okay. Put it there. Okay. Mic is good, and okay, so we need to. Okay, so we want to think about a video that is necessary just to review some concepts. It's gonna suck a little, or not suck. It's gonna be somewhat unhelpful because we're gonna talk about. Well, I guess I shouldn't say it's unhelpful. I just have to be careful on how I talk about it. So next video we're moving on to in the what is this? The I guess general chemistry. Okay, so we're moving to intermolecular forces, which also has consequences too, but I think we've already established that the IMFs that we're going to talk about in this next video, the reason they're there are because of charge. That's the consequence of charge is what causes them. So and I always want to keep focus on avoiding as much as I can using the terminology that they're going to see in their textbooks, or they're going to read on the many great resources online. Keep bringing it back to how do we explain this when we're leaving this class and we forget the electronegativity, we forget London dispersion forces. How can we still talk about these things? And so fundamentally it is attraction, I guess would be maybe a way to think about it. Because everything I'm going to talk about with intermolecular forces are going to be attraction. So we'll say attraction and I think a really important concept to hit is that although covalent bonds, ionic bonds, they're incredibly strong, and there's only one of them. One of them is really strong, whereas this whole topic of intermolecular forces is more important to make it clear that students remember it is a bunch of small forces that come together to still not quite be the strength of a single covalent bond, allow for flexibility, but the large amount of them, a large amount of small things is still important. So how would we do this? Attraction at atomic attraction. Let's just say atomic attraction. We're going to have to, another thing we want to kind of keep an eye on, and maybe we should even set a timer for ourselves, is we have, how many of these lectures do I want to have done today? So we need to have 5 more videos. So let's say each one takes an hour. We'll be done by 10, assuming students come in for questions. So yeah, let's try to set a timer for, I want to start recording in 45 minutes. Get a little timer going, just because, let's set a timer of like 30 minutes. So we know that we need to, you know, it won't be perfect, but we need to finish it. So atomic attraction, what's our tagline for this? This is, again, trying to bring it back to more of a human or whatever, day-to-day understanding. Because charge is about how sometimes, well, I don't need to think too much about charge. And again, I guess I want to make it clear, like, this is kind of what I want my lab, or I want part of my hopes of my profession to keep working towards, is what can we add to the chemistry space online in terms of education? Because I think there's a ton of resources for like the clear definitions, the clear scientific understanding, the established way to talk about these things, but we want a gateway into these things that allows you to get to that, but utilize what you already know about the world around you, or most people experience about the world around them. Atomic attraction. So this is. So maybe I'll say like. Do people know what Velcro is? They know what glue is. Glue, Velcro. Adhesives is a big word. Politics, kind of. I could say it gets a little political. And what am I saying by that? You know, certain we'll form certain parties of like dissolves like, or like hangs out with likes. You know what? Let's just do it. Let's not judge it too much and just go for it. We can change it later. Because I think there's like this general feeling of there's a decision of atoms to group together in certain ways. And that's kind of like politics, I guess you could say, is how people make decisions in groups, or why atoms do what they do. The politics of molecules. Sure, let's keep that going. And what do we want for a picture here? You know, honestly, I just think like oil and water is a great image to start with. So let's see if we can find one. And again, because this is education, I'm pretty sure I'm good copyright wise. Not trying to make any money off of this. All right, so let's say oil, water. And I personally always like GIFs. Oh, not quite what we want. Or do I focus more on the politics, maybe? You know what? Let's just do that. Let's go back to ChemDraw for a second and just make a quick little viewpoint of this. We don't need this anymore. We don't need this anymore. We don't need this anymore. We can use a little bit of this picture is kind of nice. Nice. Like it, like it, like it. Okay. And let's keep it somewhat chemically accurate, so you can put that there. All right, this is great. I like it. I like it. I like it a lot. And good. Okay. All right, let's bring this over. Oops. Try it again. Okay, I like that a lot. And let's insert a text box. Go back to 55. Give me my blue. And again, we don't have to judge too much if, this is the best way to explain these things. As long as it's somewhat good. Look, group is probably, again, group is not like the scientific, probably best way to describe it, but I think it's a pretty good way. And I always want to consider, am I getting too far away from chemistry sometimes? I think it's like the textbooks and so many other resources do such a good job of providing the official approach to some of these things, and I'm just trying to give a little bit of a different take on almost like the anyways. Okay, stop thinking about these things. Keep working. When we mix oil and water, we can observe molecules form their own. They don't mix. Okay, so what might be a halfway good idea is to start using some colors here. Well, oil, I guess oil to me is more of a yellow, so let's do that. And water is polar, so I'm okay with, I guess, using red here. I'm losing a little bit, I think, of. I might want to at some point come back and edit these videos and really consider like a holistic color scheme. But for now, I want to at least get something made that I can go back and edit up later. When we mix oil and water, we can observe molecules form no political parties. They don't always mix. So I kind of want more of a green. And so salt, fairly ionic, so we'll leave it red. Sugar, good H bonding, good dipoles, so polar, so we'll leave it kind of red too. Okay. And let's just put in some quick pictures or GIFs. Okay, so let's say political party. Gosh, there you are. I wonder if it always goes there. Okay, so we put this here. And I kind of want to cut this a little bit. Okay, I like that. That feels pretty good. Okay, so let's bring this idea down here and say, hello, hello! All right, we're going to have a quick chat with a student. Let me make a timestamp. Okay. Make sure I can see this again. Nice. Okay. So what we need to do is... It's kind of funny. In my student meeting, I was like, dang. Don't love this, this picture quite as much as I did at first. We want to at least make sure that this, image that most students will see right away has a pretty good approximation for the hydrogen bonding we're going to talk about later. So let's fix that up. So let's bring in this a little bit. I like that better. Find where does it post it? Usually at the end of the last text box. And there's these little green things which are kind of fun. Make it a little bit bigger, mate. Okay, great. Chemists call how we separate. How do you spell separate? Separate. They are separate in terms of... They are separate groupings? And then I could move to my iPad to talk about that, I think. Yeah, let's just try to move to our iPad and get this recorded. And at the end we could come back to this and show another continuum of it's the amount of charge that separates these groups. London dispersion forces are brief appearances of charge. Dipoles are more permanent but not huge differences in charge. Hydrogen bonding is a pretty large distribution of charge, of electronegativity, and then ions are complete charges. So let's do that. Let's keep this idea of political parties. Careful to keep... I gotta be careful how many of these text boxes I connect. because it makes it hard to edit later, which we learned last night. And what is up with this green box? Get rid of that, please. Border color transparent. Thank you. To some degree, the borders are nice, but I'm going to get rid of them just for now. And let's view for a second what this looks like when it's a full thing. Because it's kind of like, okay. Talk about this image. Scroll past this. Let's bring that up a little bit. Great. And we need to bring this down just a touch. Let's add another space in there. Bring this down, bring this down, bring this up. Make it a little smaller. Great, that's by itself. And then how far can we bring this down? Right about there. Great, this one great. Okay, let's put in a quick cute image. So image stock. Okay, good example of dipole. Let's just do sugar. Well, sugar is not great, is it? How about acetone? Pretty good. Sure, we'll take it. You know what? Let's just make a polar bear joke. Nope. Sure. Love it. Okay, then we move into... Where can this be? Right at the bottom of that image. And we call this the more extreme DD party. H, bonding forces. Because I want to connect these two. They're so important to connect that really it's an offshoot. So let's scroll down. Oops. All right, so this is just a problem I need to fix overall. So I'm going to go in page setup, and let's make these like, I don't know, what's the limit? Can I just make it like 300? Or let's do 500. Can I do 500? Oh, but it messes everything up. No. All right, that's fine. Keep it for now. Move this up. It is okay. Takes a little bit more time, and we really should fix it, but... Okay, check for a second. Okay, get rid of this. We're typically at 100 when we present. Okay, let's zoom way out again. I should have done this at the start. We will for the next lecture. Okay, down, 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 down. Woo! We'll find that photo again. We'll find that photo again. Can I just do this? Let's just copy. I know it's not going to work. It's going to put it way at the bottom. All right, bring it up. This might be an argument. Oh, no, I don't. I need to always keep considering. I'm sure that I'm not using the best programs. But I need to get away from, as much as I can, tools that are, like, I love Microsoft PowerPoint. There's a lot of good things it does. Where is it? Where is it? Where's the text? All right, we might find it later, so let's just leave it as is. Let's go back to 100%, which is what we typically are at. Okay, that looks good. And then if we go into the slides, we come down, we come down, we come down, and we go here first. Great. And let's go back to our GIFs. Find out where it put it good. Okay, scary polar bear. Sure, scary enough. And then we move to ions, which are like, I wonder if there's like laser bear. Sure, great. I wonder if I can keep this idea going. What if we use this for LDFs? Because they're all building, they're all the same concept. Is there like a cute polar bear? Sure, that's nice. I kind of like that one a little bit more. And we can't really have a panda. Okay, I like these images. Let's clean it up now. Okay, so we come here, we come here, we come here. Crop this down. Okay, boom, 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 boom. And make this a little bit bigger. We want to image. What do I want to call this? It's a kind of an election, but I want to see the this thing. And we can crop it. To 4. And again, ideally we'd actually have the forces there. You know what? Let's do it real quick, just because I'm a glutton for punishment. So we'll have LDF, and I want to fit it in here. We need to, oops, come on. We need to fill it with a background. Okay, we have some questions. Hi, let me go back to my face a second. Hi, Dr. Pratt. What does it mean by post a short video of what technology we are using? Do we only record when using ChemDraw, or do we record the entire exam? What technology we are using? I'm not sure 100% what you're referring to. I'm sure there is something I wrote that's confusing. So let me go into the midterm a second. I think what I guess my quick answer is try to answer the question that's on the exam. So if I say post an image, post an image, post a video, post a video. There's only one time I think I asked you to post a video, but let's see what I said in the instructions. Okay. Oh, I get what you're confused by. And you should be ready to record and upload a short video of yourself using your own technology or the Canvas Studio. What I mean by that is post a short video of what technology you're using. I'm not saying I don't want you to post a video of you using it. You're using your own technology to post a video. Possibly if you don't want to use the Canvas like webcam thing, you have to use it on a phone. It doesn't work on Canvas. Use your phone. Record yourself using your own technology, or use the Canvas thing. So that's what I'm saying. And then on the exam, I'll be very specific in each one what I want. There's only one time you're posting a video. There's another time I think you post a screenshot, and there's another time you also you give me a photo, if I remember correctly. So again, this is a fairly open exam. It's not the Proctor U. Nice. Okay. It's not necessarily a Proctor U exam. We'll get back to that etiquette, and it's important that we are clear on that etiquette more and more. But for this exam, taking a little bit of a break and also making sure you are aware that You can use cell phones. You might have to if Canvas isn't working the way you want. So let me know if you have more questions. Next one, would it be possible for us to get an extension for a couple of days on the QTPs for this week, especially because we don't have access to the class 12 videos yet? Yep, absolutely. 100% okay with that. I'm going to leave it for the most students to encourage them to work on it on Saturday and Sunday. Well, let me say this. It's like, I think what should be clear for this anonymous student is, and it's something that I had a meeting with another person about, the due dates are completely irrelevant, really. I understand that you are probably coming into this class like with this hyper focus on due dates, that if Cam sets a due date, it has to be done then or else he won't give me the grade I want. That's not how I operate. We have on Canvas, let me show on Canvas a second. So if we look at Canvas, the point of Canvas is that, yes, there is a due date for, you know, day 12. Where is it? It's up here. Right there. It's due on, I'm not going to change this due date. Let's just leave this as a consistent, I would like you to be working on QTPs as often as you can. But if you look at the QTP mastery and learning evidence, this is due August 6th. So if you're asking for an extension, you're already granted an extension. You can, because I have the ability to check timestamps, I have the ability to see when did you view the key, assuming you didn't get it from another student. I will know when you submit something on this Canvas quiz that you attempted it and then got the key. So everybody gets, you have unlimited extensions. You have until August 6th to have any of these QTPs done. So I'm going to leave it as is. You're good on your extension, and I want other students to know that the reason this quiz exists is to give you the extension that you need. You can submit them anytime. I have timestamps for everything. So hope that helps, and we'll get back to making those videos. Okay, so we have LDF, and of course, ask questions if you're unsure still. LDF party, dipole party, hydrogen bonding party, and the ion party. Great, okay, goofy, but good enough. And group it. Can I group it? Thank you guys. Thank you for coming and stopping by my office. I really do appreciate when students stop by. It helps me get better, would you believe it? Okay, so we got the LDF party, which is like, again, all these are on a spectrum, and I want my lecture to, whether you realize I'm doing this or not, I want there to be this progression of the LDF party is, you still use the concept of charge separation, but it's the worst charge separation. So I got the worst polar bear to start. Then we're going to move to, let's make sure this looks good. Okay. Boom, boom, talk a little bit about this image, move about the next case, show this image, move to this one, show this case, move to this one, and let's get these pictures figured out. I think we need to combine these because we won't have enough space. Oops, I need to make sure this looks good. Go, let's go. Okay, done. Moving on. Paste. I wish you wouldn't go to the top, but it's okay. I guess I can deal with it. Should I post like 3 of them? Probably. See, this is why I also just need, in general, student help, because Ha! Okay, we got 3. Great. Something I did there worked, so we'll keep that on. Okay, second. DD party. Great, and then next level would not be any of these, but this little guy. So not quite a pixel anymore. So we see this, we talk about this, and then we move on to this needs to be the new top, so it'll be right there. Great. Next one. Okay, so now we're going to grow up our polar bear, so we're going to come down. And okay, we've gotten a little bit more of an extreme of the DD party. And last but not least, and we can start recording. So we are here. I should eliminate a little bit of that because it kind of is confusing. And then, okay, let's take a breather from this and go to ChemDraw and make a spectrum that we'll end with. And then last time I kind of ended with this idea of electronegativity as a spectrum, or electronegativity and that charge as a spectrum. How is this going to be helpful? What can I end this to look forward to? You know what? Let's not worry about it. And I think it will be important to show where I'm kind of approximating these forces on the scale. And so let's grab this text. We need 4 of these, 2, 3, 4. We'll put LDF party there. We will put dipoles kind of there. The most extreme dipole there. And kind of ions in each ion party. Okay, great. So we'll say LDF, dipole, dipole. How did I define them? HB and ion. And I'm not going to spend too much time cleaning this up. Let's just approximate it and save the chem draw for later. We can do a quick middling of those, quick middling of these. So you don't see this right. Well, I can show you. Oops, what happened? Okay, we're going to middle those, approximate them there. And last but not least, let's middle these. Beautiful. Okay, so now we come back to, we finish with this, and then we go to a reminder of something they've seen before. And I do kind of want to, if I like go here, yep, okay, that's, we're learning and we're burning. So we do this. We come down and we go here. What did I call it? Charges and consequences? Charge and consequences. Okay. Come on, come on. And bring in our other image, and we got ourselves, I think, an approximation of a video. Okay, let's check some things. So we're here. We go back to 100%. Good, this is how the video starts. This starts here, I go into slides. We talk about this, we show this, we talk about this, we show this. We talk about this, but could move it up just a bit. we kind of show this idea. Bring this down just a little bit. Oh, it should be its own thing. Dang. How about I just didn't increase this? That's a quick fix. Okay, go back to the top. Good. Good. Not great, but good enough. I think I've made the mistake of not looking at these at 100%. So I do want to make them a little bit smaller. Again, we won't spend too much time. And I don't need the bottom of this image. Okay, I think this is good. Start here. Go into slides. Chat. Oh, make sure that's good. Yep. Chat. Chat. Talk. 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 Done. Be able to move to paper. Good. Okay, let's take a shot at recording it. Can we one-shot it? Probably not, but I think we just have to accept whatever we do here is going to be good enough. Okay, so what can I prep on here? I can prep on here hexane. Okay, that'll be good enough. And then I can prep down here. Here. And then I can prep down here. Get some values before we go. So a big part of the discussion is using electronegativity. That's where this scale is coming from. Okay, so we will say, let's make sure our lecture looks good. Or no, we can just leave this up. We'll just leave this up. mic check, mic check, mic check. Okay, here we go. One shot, one attempt, and then we can move on. So, and let's go to recording. Okay, think about what's my opener for this. Sure, all right, let's try it. All right, guys, so now we're going to move on to atomic attraction. This is really important for us to understand that if we believe that molecules have these charges inside of them, what does that do? And we're going to kind of look at this with the lens of political parties, or why do certain people group themselves in some parties and sometimes they don't interact with other parties? Why do we divide ourselves? And how does that apply to our chemistry world? So as we kind of look at this first image that I'm starting with, you'll see something that you may have experienced before. If you've ever mixed oil and water, you would find that the oil, which is this kind of long carbon chain, will separate itself from the water it's been combined with, and depending on density, I could be wrong with the density here, but we won't check that. Usually the oil is on top and the water is on bottom. And so what I want to kind of let you guys know is, just like political parties don't like to always mix with each other, molecules are similar. They separate themselves. And so again, we know that these parties are separated, right? They fight each other. They don't want to necessarily work with each other. They're sometimes working against each other. But, you probably have also mixed salt and sugar into water and saw that it doesn't separate. You don't see the salt or the sugar on top of the water. No, it dissolves into it. And so why does it do it? Why is salt and sugar more like a group of different people coming together? What is doing this? And so the kind of big chemistry word here is intermolecular forces. And we're going to cover 4 of these groupings. And again, it's kind of like if you're voting for a party. It's like, well, which one do I want to choose? Which one of these parties best explains why molecules do choose to combine, or why do they don't? So first, let's talk about the London Dispersion Forces Party, the LDF party. And what you're going to notice is that all of these parties are kind of similar in some ways, but the LDF is the most, let's say it's not a particularly aggressive party, or maybe the political term would be an extreme party. And so if I move over to my paper, you're going to see here we have the molecule hexane. And what is really important is we need to remind ourselves that hexane does have its CH bonds going on. And of course, right here, whenever we have these interactions of 2 lines coming together, there's also an atom there, but sometimes we don't show it as chemists. And so what I want to point out here, though, is that there are electronegativity numbers for these things. So again, we're going to use, in this case, the Pauling scale for electronegativity. And you'll see carbon is 2.55, so I'll write that in. And hydrogen, on the other case, has a scale of 2.20. So we talked previously in a previous lecture that this means that we need to look beyond these lines on our picture. And let's erase that line there and instead go back to considering how the 2 electrons are more often than not pretty fairly shared here. The difference in electronegativity values is not very big, but there's a little bit of pull more towards the carbon since it has more protons, and so the electrons are a little bit found more by carbon, but overall it's a pretty fair sharing of these electrons. However, what's really interesting, and what London Dispersion Forces tells us, is that if we have another molecule underneath of it, of hexane, so we have another one of these molecules, we also can kind of look over here and say, well, if there's a pulling of the electrons towards the carbon, if we're pulling electrons here, there's a very small partial negative on carbon and a very small partial positive on this hydrogen. And so over here, if we look beyond the lines on the page for the bond in the molecule nearby, why do these 2 molecules come together? Well, in here, there is some electrons that this hydrogen is actually going to be a little partially negative, which is kind of confusing because we might say, whoa, I thought it was more towards the carbon. But just instantaneously, for a small moment, because the electrons over here were pulled towards their carbon, and a little partial positive appeared in this area on this hydrogen, we might see that these electrons get pulled a little bit closer to the hydrogen, and a little small partial positive charge appears on carbon. And so now as these molecules, let's see if I can grab this one. And so as these molecules are kind of moving around a little bit, we're going to find that these molecules are kind of like attracted a little bit more. As these charges kind of come and go, they affect each other and they interact with each other. And so this is a very small, instantaneous charge where the electrons, almost through something we've called an induction effect, is happening, but it's very small. But it is still little partial charges that are causing these oil molecules to be attracted to one another. And so not a lot of charge, not a very extreme party, certainly, and so this polar bear is a good description of it. But then we find there's the dipole-dipole forces, the DD party, where we're getting a little bit more of a polar bear, an actual, still kind of cute, still not particularly extreme, but I want to bring us away now from this kind of hexane molecule, and we're going to move into the molecule that you see below, the acetone molecule. And so as we go down here, you're going to see again, this is acetone. And once again, I'm going to pull out my scale and say, now things have gotten a little bit more interesting. Now there is a carbon here that has the similar electronegativity value, but notice how the difference in these values is a little bit bigger. There's more of a force for the electrons. Again, if we kind of look beyond these double bonds and start to see that those lines on a page represent electrons, those electrons are more often found near the oxygen, and so we develop a bit of a more permanent and larger partial negative on this oxygen and a more permanent and larger partial charge on this carbon. So again, back here, I drew them smaller. The little partial charges appear and disappear. Here they're more permanent in this political party, or this grouping of why molecules interact the way they do. And so if this is indeed permanent, if we know that these electronegativity values cause there to be more of a permanent dipole-dipole, now if we take this molecule, we start to understand why another molecule that's nearby would say, oh, I'm going to align my permanent partial negative nearby, and I'm going to have a stronger force of attraction nearby to this molecule. And so these types of molecules are attracted through their dipoles, which are permanent. The charges, the partial charge is always there, always existing here. And so we'll leave that there. And so then we're going to move into the more extreme party, the hydrogen bonding party. Now our polar bear's gotten a little bit scarier. We've moved from the cute polar bear of the DD party's representative to now the hydrogen bonding party takes more of a big adult polar bear. It's a little bit more aggressive in terms of what's happening here. And so what's really important for us to realize is that as we move away from this molecule oxygen, we can remind ourselves that the difference in electronegativity was 2.55 for carbon versus on the Pauling scale we saw about 3.44 for oxygen, and so about a difference of 0.9. What if that difference got bigger? What if that difference got more extreme? Well, as we move down into water, what are the differences here? Well, water, again, we know oxygen has this value of 3.44, but notice how hydrogen, we knew from looking at our first political party, the LDF party, that it's even bigger. And in fact, this difference is now not even 0.9, but we've got a big difference, the biggest difference we've seen yet, 1.20. And so in this case, we can say, wow, this is the biggest difference in partial charge we've seen yet. So I want to draw these even bigger. And this is so big that when we have another molecule of water nearby, there's actually even a partial bond. I do it as a dotted line between water is so attracted to this other hydrogen that the forces between water is starting to verge on the level of interaction of a bond, which is stronger than these intermolecular forces are. And so again, it's a large charge. It's a large charge. And so this water molecule, as it's moving around the system, it has its partial negative, feels the partial positive of hydrogen, and almost forms a bond to it. And again, this is the largest difference in electronegativity we've seen yet. And so you might be able to kind of expect, well, what's coming next is the biggest difference in charge. What happens when you're not partially charged, but what is an ion? An ion is a full charge. This is the scariest, most extreme, quote unquote, political party, the ion party. If LDF was fairly neutral in its leanings, the ion party is very extreme. And so we'll return to where we started this lecture, the idea of why the heck does salt dissolve in water? What I want to point out to you is we don't have partial charges. We have a full positive charge on the sodium cation when it dissolves, and we have a full negative charge on chlorine, and the hydrogen still has its large partial positive and its large partial negative. But we can now think about these interactions are even bigger. We have a full charge interacting with a full partial negative. We have a full negative interacting with a full positive. And so what I would want to remind you is that the concepts in this video are building on a different video, Charges and Consequences, where we saw that charges themselves are on a bit of a spectrum. If we're neutral, but we can go partially negative or lots of negatives, or partially positive and lots of positives. The forces I talked about in this video are also a spectrum, and there's still a spectrum of charges. So when you have these full charges in your interactions, you're more dealing with the ion forces. But when there's these occasional charges, these smaller partial charges appearing and disappearing, you're more in the London dispersion forces. But all of these parties are still part of this polar bear concept, this polarity concept, where we go from LDFs, dipole-dipole, hydrogen bonding to full ions. Okay, a little bit of a rough video, but I think that's good enough to post. So let's find it, make sure it's good. This is really important for us to understand that if we believe that molecules have these charges inside of them, great, I think that's the one, IMFs. Go to Canvas and upload. Don't need you, push you over, go here, go studio. Okay. Oops. I need to resave. This is not IMFs. This is now angles in big molecules. And why I have to say big molecules, I can't say macromolecules, is I just want to be careful that Emery did say if you're going to make your own videos, make sure not to follow necessarily all of the things that we do. And so I want to respect that and make sure that I do that. But I'm going to need, and this is not super good, but it will start. We'll start. I wonder if there's a shape for this. Well, this is basically what I need. And again, there's a part of me that's like, well, I should make a video on Newman projections. No, you can't. You can't right now. Flip that 180. Approximately 180. And let's send to the back. Great. Okay. Let's highlight this angle. And let's highlight a quote-unquote more imaginary angle, or not imaginary, another type of angle. Just a little bit bigger and dot it. Nope. Nice. Okay. And now we can highlight this angle. There's a way to do... Oh, I bet it's arrows. I bet they use arrows. And you just take off the arrowhead. It's kind of fun. ChemDraw is one of those like programs that the more you play with it, the more you realize how people probably created some of these things. And let's just do a period for the eye. Group it. And I am a little bit of a... I like to put some eyebrows on mine. And I think the joke we will quote-unquote attempt to make is that you have this one, and let's group it. Let's flip it. Nope. And I want you to be a little bit more square. squinty. And I think again, there should be a whole video on bond angles and Vesper theory. Come on, ungroup, please. Ungroup. Do not interpret chemically. Come on, what's up there? What are you finding up here? Can I get rid of it? Oh, that's it. I know what it is. Nope. Close. It's because it's a period, that's why. Anyways, great. Makes sense. In. You know what? I don't even think we need the text. We'll just vocalize it. So leave that. Group, middle 'em. Nope. Undo, center 'em. Ooh, undo. Center 'em. Okay, good enough. Bring it in here. Okay. Nice. We're going to want a new page. So this is what they're used to. This is new. Okay, let's grab a text box. And, you know, there's a part of me that wants to be goofy and say, in previous videos you've seen, just to prepare for the video that needs to be made for Chem 150 at some point. Okay, great. So, love it. Let's go into slide mode. Ooh, careful doing too many of these. So great, leave it. So again, kind of a rough shot of another video, but this one I think will be fairly easy to do. And again, we're starting to lose the quality of the videos, but students need this information, and so at some point I have to just give up on, or not give up on, but remind myself that at the end of the day, it doesn't have to be perfect. But starting here is very important. So, okay, next video, and part of me does want to upload these to YouTube, but I'm very nervous to do so a lot of ways. So anyways, okay. I think we're recording. It looks good. I see Mike. Okay, so let's try it. All right, so this video is going to focus on how we might need to add a little bit of a new perspective to some ways we look at molecules. And so you're pretty used to, at this point, looking at a tetrahedral, an sp3 center, and saying that angle right there and other angles in this molecule are 109.5. Our eye can look at these things and we can start to see these things. But it's important for us to look at some other angles, and these might widen our eyes a little bit, but we can look past a molecule and start to see there are other ways to consider angles in a molecule. And so I want to just kind of remind us that, in general, being able to see different perspectives on things is really important. It allows us to ask different questions or have new understanding of things. And so, of course, here we see the small man and the big woman, and then suddenly the big man and the small woman. And it's really just a matter of, in this case, forced perspective. So if we take this forced perspective idea, what are we working on? What angle might we take on this molecule? This is a very important molecule for our discussions that we've been looking at in these big molecules, where we start to talk about the formation of the amide bond, or a bond that's very common in proteins. And so if I switch over to my paper, we might say, well, when I look at this molecule, I know that I have a double bond here, and so any angle coming off from here that I might kind of show us here, that angle we're going to say is 120 degrees. And that's because this carbon in this drawing is an sp2 center. And then if I have, of course, my nitrogen here with its lone pair on it, and it itself will also have bonds to other things. Here we can even zoom down just a little bit. Bonds to other things here, and bonds to other things here. I'll just label them as R groups. For now, R groups are, of course, carbons and hydrogens. And here we would say, well, this angle, because this nitrogen is sp3, we might say it's 109.5 degrees. But this is actually not the case. What's happening in this molecule is we need to shift our perspective a little bit. Rather than only seeing the molecule like this, we need to also remind ourselves that these electrons are pretty important, because there's a resonance structure that I can draw that shows these two electrons going here and these electrons going here. And so now our perspective on this molecule might change a little bit. Because what have we done to this group here? Now a student might say, well, if this thing is still connected to two R groups, and yes, it deserves a partial, or it deserves a positive here, and because these electrons moved, we now have a negative up here. Now a student would say, well, looking at this picture, I would assign this nitrogen to be sp2, changing now the bond angle from before we saw it as 109.5 to seeing that in another perspective, we could draw a picture that shows it has 120 degrees. And so because this resonance structure exists, the amide bond is actually quite planar. And so when we look at the classic, let's say we have a, let's say here we have the amide bond between different groups. we're going to find that all of these molecules, 1, 2, 3, right? We know all of those are, or we know all of these are in the same plane because this is sp2 in the picture we typically draw. But what we want to add to our perspective today is that if we see the partial double bond that's here, there's kind of this, let's say, double bond character. It has a little bit more double bond character to it. Then we would also add that this and this, all of these atoms are in the same plane. Because both of these centers, both the carbon one here, and when we see the resonance structure for the double bond character to this nitrogen, it is more sp2, meaning all of these are in the same plane. And in your amino acids, you're only going to find that sometimes over here, there are still some sp3 centers that allow us to break out of this plane. And so we have this new view on these bond angles. It's not just that the bond is 109.5 for that nitrogen. Instead, we need to shift our perspective to see that it really is a more double bonded character. This has all of these atoms in the same plane because these electrons are very good at resonating with one another and creating more of a double bond. So now all of these atoms are in the same plane, and only at that little purple R group might we sometimes find out here we might still have a little bit of things that go outside of our plane. And so this new perspective is quite nice and helpful for understanding amino acids. But to keep going, we need to also consider that we don't just have to look at bond angles between three atoms. Chemists have developed another way to look at bonds that look at four atoms. So this is called the dihedral angle. Now this is where our eyes might start to widen a little bit, and so I want to bring us back to, think about a clock where only one hand is moving on the clock. And if we stacked two of those together, how could we look at those two hands moving and possibly see an angle between them? And so this is where we're going to get into the dihedral angle. So again, let's take a very, very simple molecule and really focus on only the important parts of it. So right here we have the molecule ethane. And if I expand ethane, we know there's no issues with resonance structures. We know there's no partial double bonds like we saw in our previous example. And instead, we typically draw the molecule in its most stable form, which has still an sp3 carbon here and an sp3 carbon here. But we can look at the bond angle between this atom, kind of shift our perspective back, and now we can see another angle if we look with our eyes maybe widened a little bit from this perspective. And so I'm going to take this kind of picture here, and I want to redraw it in a way. Let me see if I can. And we're going to kind of And so we're going to take this molecule here, and what if we shifted our perspective, where we moved it so we were looking at it kind of from its head on, where we started to put those carbons behind each other. And so you've seen this before in previous classes or videos, that we call these things Newman projections. So now, instead of looking at it from this direction, I'm going to take this red carbon and move it behind my green carbon. And so what this looks like is I'll put my green carbon on front, and I'll still respect that we have these angles of 109.5 between them, and I'll draw a little circle, draw a little circle, draw a little circle, and now behind it I have the red carbon with its bonds. And so behind this one now, I can measure different angles. I can measure the angle here. That would be of 4 atoms. I can measure the angle here. That's still 4 atoms. And let me move this up a little bit. Or the one I pointed out earlier, well, it's not very clear now, but the angle I pointed out earlier would be the angle from this atom to hydrogen to this one down here. And so maybe I'll make it green instead. But that angle, what angle is that to you? It's a straight line, and so it's 180 degrees. And so this is how we look at, and you've probably seen this before, and thank you to Master Organic Chemistry for already creating a great resource. This is on their website. We're able to see that as we look at different rotations of the dihedral angle, from 60-degree rotation, 100-degree rotation, 180, all the way through, there's actually different energy levels for these conformations of these molecules. And so we're going to be able to take this concept and apply it to what we see in our body. Okay. Again, kind of a rougher video, but we're getting there.
Welcome to this video on chart.
That's not it. Was I not recording? I thought I was recording.
Alright, so this video.
Nice. Okay, let's get rid of this one, delete it.
Alright, so this video is going to focus on how we might need to add a little for these.
Okay. Angles. Go to canvas. Let's go to